Okay. And so, uh, uh, what I would love to talk with you about today is some work that we've done and published recently, uh, just taking a closer look at ion dissociation in ionic liquids and ionic liquid solutions and trying to get the most possible information we can out of the data that's available. And so to do that in the talk today, I'll just start out by talking a little bit about what we mean by ion dissociation and the traditional way of calculating ionicity in ionic liquids, and then introduce the approximate method that we've been using, which lets us use more readily available data, and then just touch on a few of the results for neat ionic liquids, aqueous ionic liquid solutions, and non-aqueous ionic liquid solutions. Most of this is actually in a review article in Chem Reviews that came out late last year. And this work was done by one of my former PhD students, Oscar Nortis, really fantastic fellow. He's now at the University of California, Santa Barbara, doing a postdoc. So we all have a very good understanding of how salts dissolve in water from, I took this from middle school chemistry, right? So we know that, for instance, sodium chloride, the hydrogens in the water interact with the chloride anions. The oxygen in the water interacts with the sodium cation and helps to dissolve those into water. So it causes a dissociation of the cations and anions. Of course, the ions are held together by electrostatic forces, but the solvation by the water, for instance, overcomes that. And we can have, depending on what the salt is in systems, we can have other species, for instance, contact ion pairs or solvent separated ion pairs. Ion pairing is more prevalent for highly charged ions, especially small, highly charged ions like the lanthanum and calcium. Uh, Ion pairing is usually not very significant for monovalent ions, of traditional monovalent ions, except for little bitty tiny things like lithium. And if we wanted to, we could describe the dissociation by an equilibrium constant, shown here in terms of concentration, but of course we know that it's not really concentration, that equilibrium constant should really be written in terms of activity, so that it includes the non-idealities. So then we can move to start thinking about, what about the cations and anions that we're all most familiar working with, that, as I tell people, they tend to be more organic-y. So we would anticipate that because the charge is distributed on most of the cations and anions over many atoms, we would expect ion pairing that would cause ion pairing to go down. On the other hand, we could have attractions between parts of the cation and the anion, for instance, hydrophobic parts like alkyl chains that would go to increase ion pairing. So in ionic liquids, though, we can go all the way from a dilute concentration in water, for instance, but then all the way up to the pure salt system. And so, we of course then ask ourselves, how do we define an ion pair in those kinds of systems? no ion is solvated in the pure ionic liquids because there is no solvent. Okay. Uh, but are there free ions? And we all know the answer to that it's yes, because even pure ionic liquids conduct, um, they have uh, conductivities, measurable, in fact, some cases quite high conductivities. So, we really need to ask ourselves, how do we think about ion pairing in ionic liquid and ionic liquid solvent mixtures? When we can have this concentration going all the way from something very dilute to the pure ionic liquid. And so I personally think the best way of representing this, and the way that really uh, is very akin to what I will end up showing you, is the Walden plot, right? Where we plot the log of the molar conductivity as a function of log of the inverse viscosity and compare it to that ideal line. Of course, it's been pointed out that that ideal line is not really, even zero point 0.1 molar potassium chloride is not really completely dissociated, but it is mostly dissociated. And so then you can plot the ionic liquids, how conductive are they for a given viscosity, and see how far below that or above that ideal line they are. Uh, uh, I do want to point out that I think sometimes when people look at a Walden plot, they, they think, and they, think of uh, how ion paired the ionic liquid is. The idea of an ion pair, people tend to have a static picture, whereas the Walden plot really emphasizes to us, because this is conductivity and viscosity, it really emphasizes that this is dynamics. And here's are some pictures taken from some simulations done by Ed McGinn's group. And, you could say, okay, um, at the beginning here, the anion that's closest to the cation is the one that I just put a circle around. And then as time goes on, everybody moves. And, okay, so that one is still the pair. So that pair is still intact. But as time goes on, then, that anion will move out and another one will move in and be the closest anion. And so you can define something like a ion pair lifetime based on these kinds of simulations. Ed also, they defined an ion cage lifetime, right? So that's where you say, okay, what are the anions around a central cation, and then look how that evolves with time, so that, how long is it before, one of those go outside of a cage of a given size and somebody else moves in. So you can define these ion cage or ion paired lifetimes. And they actually showed that diffusivity, or ionic conductivity calculated from diffusivity, actually correlates nicely with these ion pair and ion cage lifetimes that they got from molecular dynamics simulations. So all I'm saying is, even though I think when we talk about ionicity, how dissociated an ionic liquid is, we may get a static picture. We all just need to keep reminding ourselves that it's really dynamics that we're talking about, and that ionicity is averaged over some time period. So what we've traditionally done in ionic liquids is define the ionicity as the ratio of the free ions over the total ions. And of course, this is a lot easier to do than to calculate an equilibrium constant, where we would really need to know the non-idealities in order to express that equilibrium constant in terms of activity. So just the number, all right? So the time average ratio of the free ions to the total ions. And the way that this has been beautifully measured is by using impedance spectroscopy to get the ionic conductivity. which tells us about the transport of just the ions. So just the ones that are not paired, right? So anything that's charged will contribute to the ionic conductivity. And then using pulse field gradient spin echo NMR to measure self-diffusion of cations and anions. And that self-diffusion doesn't know whether or not the anion or the cation is paired or not paired over the time frame of the measurements. And so that tells us about the movement of all of the cations and anions. So that's related to the total ions, the ionic conductivity to the free ions. And so then we take the ratio of those two to get the dissociation. The conductivity measurements, as many of you have done, are relatively easy measurements, don't require very much sample, and so you can measure those free ions. The pulse field gradient NMR experiments are a little bit more time consuming. And of course, you've got to have your NMR. And you got to be able to do fluorine, for instance, if you got bisphosphoramide anions and so on. So these are a bit more labor and time intensive, certainly than the ionic conductivity measurements. And for this reason, there's sort of a limited number of ionicity values reported in the literature. Here are some ones from 2006. And this is a series of dialkyl imidazolium bistrifluamides. And going from methyl-methyl, ethyl-methyl, all the way up to octyl-methyl. And you can see that as the alkyl chain, that second alkyl chain increases, this ionicity, or the fraction of the ions that are dissociated, decreases. And the interpretation, of course, is that this is due to the van der Waals interactions between those alkyl chains. The methyl-methyl, and even the ethyl-methyl, they're about 75% of them are in pure IL dissociated, where it goes down to about 50% in the octyl-methyl and imidazolium bistrifluamide. All right, so as I said, the pulse field gradient NMR is kind of experimentally costly and time costly. So is there a better way? And really the better way is suggested by the Walden plot, and not a better way, an alternative way, all right, which is to use the Stokes-Einstein approximation that the diffusivity, which is what you're measuring with the NMR, is inversely proportional to the viscosity. And of course, measuring viscosity is very easy. So if we could use the viscosity instead of the diffusivity, that would give us a lot more data to work with. Now, the disadvantage of this is that you have to assume some radius, all right? So you have to assume some size. And Stokes-Einstein assumes that we've got spheres, and we know that the cations and the anions of ionic liquids are not spheres, but nonetheless, we went ahead and forged forward. So if you do this, getting the diffusivities, not from NMR, but from viscosities, we end up with this ionicity, the ratio, the fraction of free ions, as being dependent upon the conductivity, that same as before. But now we need the viscosity. We also need the density, because the conversion, you need concentration, right? So we need the density, and then, as I said, these estimates of the size of the cation and the anion. So to just emphasize, now we need to get an estimate of those size things, but the experimentally measured things that we need are simply viscosity, density, and ionic conductivity, all of which are relatively easy and quick in order to do the measurements. there's many ways that we can estimate the size of the cations and anions. We've used an incredibly simple method, which is just to use group contribution methods developed for the UNIFAC and UNIQUAC uh, activity coefficient models. So just adding up groups, and this, of course, these values have been done for groups in ionic liquids. And so that's the method we have used. There's many other possibilities. We realize there's pluses and minuses to each estimation technique for these sizes. All right, so now just to look at some of the results for the pure ionic liquids. And so here, first thing we want to do is compare this approximate method using the viscosities to the values that you get when you use the pulse field gradients Brennecke NMR. And so these are the same data that I showed you earlier. So now here we're comparing those values from ionic conductivity and pulse field gradient NMR to the values that we get with our approximate method. And so you can see that the values are all within about 10% or even better sometimes of the values from the NMR. And from our experience, actually the uncertainty in those NMR diffusivity measurements are probably not a whole lot better than 10%. So it seems to us that not only is the trend good, but that quantitatively, this is a pretty good estimate of this ionicity. Here I'll just show you a few other trends. And so now what we're doing is just taking systems for which there's only density, viscosity, and conductivity data available, for which there is no pulse field gradient NMR diffusivity measurements. And so here, I'm just showing you that same data, all right, but showing it with in comparison to ET30 values that have been reported for these ILs. So nothing new here, just decreasing ionicity, decreasing dissociation with increasing alkyl chain length on the cation. Now, if those are for bistriflumids, so what happens with cations that are paired with other anions? And so here we're showing a comparison of pyridinium cations with short versus long chains as we go across, all right? And the decreasing ionicity with increasing alkyl chain length is certainly true with these pyridiniums with the bistriflumid anion. But when you pair it with something like dicyanamide, then you can see that the ionicity is not very dependent on the alkyl chain length. So, how the alkyl chain length on the cation influences ion dissociation, it really depends on the coordinating or non-coordinating ability of the anion. Here's another one. There's two concepts in this one. So here we're plotting ion dissociation calculated for the densities, viscosities, and conductivities for three different alkyl chain lengths, right? Ethyl, propyl, and butyl. But we got a comparison of the hatched and dotted ones that are circled here, and those are where we've got the dialkyl versus trialkyl imidazolium, where you're blocking that C2 hydrogen, putting a methyl on there. And when you block that, then the dissociation increases substantially. And that makes a whole lot of sense, right? Because you're blocking that interaction between the acidic hydrogen in the C2 position and the anion. The other thing that's shown on here are just three different versions of the pyridinium. One where you've got a methyl in the 3 position, the other one in the 4 position, and you can see that where we've got the presence of and the position of that methyl doesn't really change the ionicity at all. Here's where we're keeping the anion the same. So all of these are with bisphenolamides, and with as many different cations as we could find the data for. And I must say, we took most of all this data, we loaded it out of ILThermo. So thanks to NIST for having ILThermo, where we accumulate all these data. And a few of these, there are NMR results, which are also shown on here, but most of them not. So you can see from where we go from a very high polarity to very low polarity cations, and that changes our dissociation for the high polarity guys below 60% to the low polarity guys that make it above 80 or almost 90% ion dissociation. All right, here's one where we're looking at the anion alkyl chain length. So not the cation alkyl chain length, but the anion alkyl chain length. And so here we've got methyl sulfate going all the way up to octyl sulfate with EMIM. And you can see that there's very little change in the ion dissociation with the change in alkyl chain length on the cation for this relatively strongly associating sulfate anion. All right, I've done the opposite for you. So now I'm keeping the cation the same, and I seem to have not put it on here. I think this is EMIM, and with a wide variety of different anions. And once again, here, looking at the polarity in terms of the beta parameters from Camelot-Taft, which report on polarity, on hydrogen bond, well, basicity or hydrogen bond acceptorability. And you can see how we have very low ion dissociation for the ones that have very strong hydrogen bond acceptorability, less than 40%, all the way up to the thiocyanate, which once again is up 80% or more. All right, and this shows, I think, a very interesting result, which is that you have to be careful with the pulse field gradient NMR values because you can have convection problems when you do them at elevated temperatures. So here we compare for two different systems the ion dissociation that you get from our approximate method using just the density, viscosities, and conductivities versus the ones that you get with the actual NMR measurements. And the actual NMR measurements suggest a large decrease in the ion dissociation as you increase the temperature. And that is not reflected in the version for the density, viscosity, and conductivity measurements. And as I said, this we really think is consistent with what other people have pointed out, is these convection problems, so that the diffusivities at for the NMR measurements are actually erroneously high. So that you're not getting good estimates of this ion dissociation with increasing temperature. All right, so just the next thing I wanted to look at is where we've got ILs dissolved in molecular solvents. And, certainly we can think about, the ionic liquid, pure IL, as we add more and more water or more and more other solvent, we could, be going to aggregates or triplets or contact pairs or contact ion pairs or solvent separated ion pairs, or all the way to our free ions. And so what does this look like with the density, viscosity, and conductivity data? Well, once again, we first want to compare with the NMR results. All right, so this is this is a system of water and ethyl sulfate, and over the relatively narrow composition range, the dissociation stays around 60%. And so here, oh, I got a little more here on here than you want to know, but here, if you do the calculations from the Stokes-Einstein version that I've been describing here, is the one in the middle, and you can see that both quantitatively and qualitatively, we get the same values as you get from using the NMR diffusivities. I'd say that these values are maybe a little, this agreement is maybe a little deceptively good. If you look over a wider range of comparisons, here we're comparing some of the EMIM and BMIM methyl sulfates and ethyl sulfate. And you can see that there's a bit, I mean, the trends are fine, but there's a little bit larger disagreement. So I'd say in general, the estimates from the viscosities for the ion dissociation are not quite as good in aqueous solutions as they are in pure ILs. Nonetheless, we proceeded, and here are actually all EMIMs with a variety of different anions in water, all the way from chloride, which is the one at the top, to triflate, which is the one at the bottom. But you'll see that they all do something very strange. And that is that the pure IL is on the left, right? So as you start adding water to the pure IL, their ion dissociation doesn't change very much at all until you get pretty much a lot of water in there, maybe 80% mole fraction of water. And then the ion dissociation appears to go down. And then when it's really, really dilute, then it starts going up again. And these are actually some measurements we took where we took a lot of the data in that very dilute region to see what the heck was going on. And so here are actually the viscosity numbers. This is for triflate, trifluoroacetate, and ethyl sulfate. So you can see what the viscosity does. It makes perfect sense. And then over here is, of course, the conductivity, which still makes perfect sense in that as you dilute with water, you are decreasing the viscosity. So you're increasing the conductivity, but eventually you have so few charge carriers that the conductivity starts going down. But these data are, are definitely accurate within a couple percent. And when you do it, then you get this very large, strange dip in the ion dissociation. And so after looking at a number of these systems and thinking about it a bit, what we think is happening here is that our assumption that we have constant ionic radii is probably not correct. And that, of course, is what we're assuming. We're assuming values for the size of the cation and the anion. And so when we do that, it shows this dramatic decrease as we become more and more dilute in IL, all right? And then eventually it does go back up when we get very, very dilute, that would be consistent with complete dissociation at infinite dilution. And we're not aware of any ionicity estimates from NMR in this composition range with which to compare it, right? Um, what we really think is that uh, the the two possibilities. One is that in that region, the cation and anion are dragging water molecules with them. But what we think is probably more likely is that as the water content becomes larger and larger, the ionic liquid, things like the EMIM, right, it's not real comfortable in water, and that we actually end up getting things like triplets. Um, so that the effective size of the diffusing species actually is larger. And so this is just, what would have to be happening if, at the other extreme, if the ion dissociation was constant and we used the data to calculate what the radii would be, and you can see that the radii would have to be increasing a little bit. So in this region, we think this is a situation where the assumption of constant ion radius is probably not real accurate. So the last thing that I wanted to talk about was non-aqueous solutions. Uh, and uh, and here's where we did find some NMR data with which to compare. Um, so this is, bistrinyl mid, all right, in a rather low dielectric solvent. Um, and as you increase the amount of the solvent, the ion dissociation just keeps going down, 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 down. All right. Um, so this low dielectric solvent is not able to solvate the ions. All right. Uh, and this is captured very, very well by both that's what the NMR plus conductivity tells us. And when we use the viscosities, it tells us exactly the same thing. So very good agreement between the pulse field gradient NMR and the density viscosity conductivity estimation method, that this ion dissociation decreases dramatically with increasing solvent. And there's essentially no ion dissociation in the dilute IL region, not able to solvate the cation and the anion. Here is a more higher dielectric solvent. We've got acetonitrile here, and it is sufficiently polar to be able to support ion dissociation in the dilute IL region. And you can see this by the increasing ion dissociation as you go to infinite dilution. Once again, you see this apparent minimum in the ion dissociation in the 90%, 95% region. And so once again, it's possible that we may have this aggregate formation, or a case where the size of the effective diffusing species is larger in the acetonitrile, just like it is in water. And so you can see here just a couple different ionic liquids in acetonitrile, where, more or less dissociated depending on the, here it's different cations and different anions. Here's a single ionic liquid. So here's our BMIM PF6 in a series of different solvents with a wide range of dielectric constants. And you can see that all of these, except for water, right? So water's just got a few data points over here in the concentrated IL region. But all the, that one looks like it's going to be staying, highly dissociated, which is what we'd expect. But all the rest of these guys with dielectric constants 20 or less have the decreasing ion dissociation with increasing solvent concentration. It looks like the ones that are above 10 may be leveling off. So if you look at the acetone and the pyridine, those two look like they may be leveling off and not going all the way to zero. Here's similar observations for BMIM BF4. Here we've got the water across the whole composition range, but you can see the dichloromethane and the ethanol ion dissociation decreasing substantially with increasing solvent concentration. So those are the things that I really wanted to share with you today. You can find out a whole lot more systems, hundreds of systems, by going to the that ChemRev article. I think that ion dissociation in ionic liquids and these ionic liquid solvent mixtures are not just interesting, but important, because they do determine key physical properties that are relevant for a variety of applications. I think the benefit of what we've shown here is that you can get pretty decent estimates of the ion dissociation of ionic liquids and ionic liquid solvent mixtures just by using density, viscosity, and ionic conductivity measurements, which are much easier and much faster than the NMR measurements. We've demonstrated a variety of different trends for the pure IOLs, the aqueous IOLs, and the non-aqueous IOL solutions, of which I've shown you a couple today. And we can then use this as a design tool for selecting and designing IOLs and IOL solutions, and potentially even mixtures of IOLs, especially important for electrochemical applications. This method was originally played with by one of my students with Mark Stothair when we were at University of Notre Dame, Luke Simoni, who's currently with Moores. He had just put it in the appendix of his thesis and had never actually published it. And then we realized that there were a variety of folks interested in this enough that they were citing the appendix of his thesis, and that's when we got a bit more interested in it. And so, as I said, it's been Oscar Nordness who's really forged forth and collected and analyzed all of the data and literature that we could use for these calculations. And I got lots of extra stuff. So, so with that, I would be happy to take any questions.
Okay, thank you very much, Professor John Brennecke, for this very, very good presentation. Now is time for questions. So you can raise your hand in the Zoom panel, bottom reactions. You can raise your hand, or you can actually write down your question and we can read it for you. Dr. Christoph Hell.
Yeah, hi, Joan. It's amazing. So thanks for this very, very nice talk and these very good results. And always I have some fear about that, because I wonder or I wonder if we have been doing the right way in thermodynamic modeling these ionic liquid solutions by assuming that they are neutral molecules, or that others that uses approaches where they consider it as completely dissociated. So none of that is correct, and we always have to consider both, right? So we always have to consider it as a mixture of ionic and of neutral components. And so that's what I got from your talk, and that's what I think what we should do really in the future to take into account this as now as we have the data. But so congratulations on that. I think it will have a huge impact in the future. But what came to my mind was about you were showing about I think there was a plot where there was a minimum in the in a pure ionic liquids when you changed or when you varied the anion chain length.
Yeah, that was the, I think that was the sulfate one, right?
Yeah, so can you explain? So I expected that there is this decreasing dependency, but suddenly it then increased again when you further increased the anion chain lengths. So do you have any explanation on that?
I don't, and I'm not sure that the change was big enough that I would be confident in saying it was real, right? Because a lot of times, you know, we do have this 10% or something uncertainty in the viscosity, right? The, you know, the densities are beautiful and the ionic conductivities are 2%, you know, but in many cases, the viscosities, depending on the water content and stuff, um, you know, I'd say they're more like plus or minus 10%. And I think that's about how much that change was. So I'm not willing to say it's real. But yeah, it'd be interesting to maybe do some careful viscosity measurements, and you know, where you were confident that you were, you know, plus or minus a couple percent on the viscosity, and see if that really is borne out.
Okay, I see. Thanks.
Yeah, and there's a question in the chat saying,
Yes.
I think it's better to use electrolyte-based models for thermodynamic property calculations like the electrolyte NRTL rather than classical NRTL? And yes, my answer is yes. And in fact, that was the reason why Luc Simoni did this 10 years ago, or more than 10 years ago. He was using electrolyte NRTL to measure liquid-liquid equilibrium, where, you know, one of the phases was an aqueous phase, and he wanted to, you know what should he use as the you know, dissociation in using in the electrolyte NRTL, and that's where he used the estimate and developed those models. So yeah, I think your suggestion is a very good one. That electrolyte NRTL is definitely better than classical NRTL. On the other hand, we all know that we have lots of systems, you know, LLE systems even, where, you know, we've been able to fit them with classical NRTL, but we just need to appreciate that it's, you know, it's an, you know, we're not really representing what's really there, right? You're getting a good fit for you know, an empirical fit to data, which is incredibly useful, but it's not necessarily, you know, really representing the real system.
Yeah, thank you very much. Any other question from the audience? You can raise your hand, or you can, yeah, Susan Perkin.
Hello, thank you very much, Professor Brennecke, for this very nice talk and for taking the trouble. I found it very interesting, this dip in the ionicity with concentration. And I think that if we flip the axis so that the mole fraction of water is increasing, then the shape is very reminiscent of all of the activity coefficient data that's measured in regular electrolytes and water. Theory or the other theories that explain this shape for activity coefficient. If you don't mind me asking also a second question, which is connected, something I find very interesting with the results you've shown throughout your talk is that although there are some variations in the ionicity with all the parameters that you showed, anion and cation length and so on, essentially the ionicity is quite similar in all cases. So it's sort of invariant with most parameters at a value of sort of 2/3 or somewhere around half. What is it about ionic liquids that means that that's basically always the same?
So, okay, so yeah, you were breaking up a little bit on your first comment,
Yeah.
but
Sorry.
right. So I agree that a lot of the models for the activity of dilute salts with increasing concentration of the salt are probably trying to explain, because you do get pairing in inorganic salts too as you increase the concentration. All right, so it's not like this is completely different. So I agree with your comment there. Your second comment was why everybody's 60%. Yeah, no, halides are not. Right, so chlorides and bromides and stuff, those guys are pushing 95%. So if you have in water, right? So if you have highly charged small ions, then they do become much more dissociated. But I think with the types of cations and anions that we use for making ionic liquids, they tend to have some degree of van der Waals interactions and other interactions, right? That cause the cations and anions to stay partially together. So I think it's just the choice of the anions and cations that tend to have distributed charge that make liquid salts, right? But the halides are higher.
Thank you.
Thank you very much. Any other question? Elsie.
Professor Andiavot has raised his hand.
Hey, Andy.
Hi, Joan. How are you?
I'm pretty good.
So I was starting to do a very long type into the chat and realized it was easier to ask the question. So what we've obviously published in the past is this concept that in fact ionicity doesn't exist, and what's different about an ionic liquid is that you've got very big ions and very small holes, and that what limits the motion of ions is the fact that the liquids are very condensed, and so there isn't anywhere for the ions to move. And the problem that I have with this approach is that the Nernst-Einstein equation and the Walden rule only work at infinite dilution. And so if you look at the Walden rule, it's basically a plot of the Nernst equation at infinite dilution.
That's right.
And so what you should be plotting is, instead of plotting molar conductivity, you should plot molar conductivity, molar conductivity against fluidity. It should be molar conductivity against fluidity divided by ionic size. And if you do that, then all the ions then move back to your ideal line. But it's just a consequence of the size that you see this change in ionicity. And we've obviously published this a few times, but it's not getting any traction. But it's a different concept. And so what we've said is that the reason that Nernst-Einstein equation works is because it's not that we've got different numbers of charge carriers, but that we've got different numbers of holes, and the holes are the limitation in terms of the mobility of the ions. So what you're effectively saying is that roughly 1 in a million ions in your liquid have got a hole next to them which is big enough to allow that ion to actually move. It's a reverse way of thinking about it. And it's like those number puzzles, you know, where you've got 1 to 15 and you've got to move the squares around. What's limiting you is not the ability to move the squares, but in fact it's the ability to move the holes.
Yeah, I mean, what you say makes a lot of sense. I don't think of it that way, but maybe I should start thinking harder about it that way.
There's about 3 or 4 papers we published on the topic. I can send them to you, but it's a different, it's a vexed topic. But the problem is that this idea of ionicity really depends upon this use of the Nernst-Einstein equation and NMR. And I know why people are doing it, but the problem is that the Nernst-Einstein equation doesn't really work apart from at 0 concentration.
Yeah, I think you bring up some really good stuff, and I think the rest of us should all go think about this a little harder, including me. Thanks for sharing it, Andy.
No problem.
Thank you very much. Elsie, we have something in the chat.
I have a comment, please.
Sorry, I was silenced. Professor Zainab asked, good day, thank you for a very interesting presentation. I want to mention that the physical properties was described very well. I want to ask which literature sources of yours I can read about petrochemical catalysis and which free programs we can use to make physical calculations on ionic liquids.
Okay, I'm not sure. Well, okay, so my group doesn't do catalysis, so I guess that you wouldn't find any of the literature sources of my group that does anything about petrochemical catalysis. That's certainly, there's lots of great stuff out there. And free programs used to make physical calculations. We don't have any programs available, but in all of our papers, we describe the equations, and none of the modeling and stuff that we do requires anything very seriously complex, so that you can just make your own from the things that we put in the paper. I know that may not be very helpful, but that's the best I can answer there.
Thank you very much. I think we have room for one more question.
I have a comment, please. Yeah.
Yes.
Yeah.
Okay.
Thank you, Professor, for the nice talk. This talk was about the ionicity, diffusivity of ions and ionic liquids and their aqueous and non-aqueous solutions. But when we talk about their practical application, like in batteries or in supercape, then many other things come to be considered, like the environmental issues and the what is called the hazardous effect. And we are seeing that the TFSI or lithium TFSI are fluorinated, and it has one of the big problem during recycling and during the battery combustion and explosion. So what are you thinking? What would be the alternatives, and how we can control or mitigate this problem? Yeah, please comment on.
All right. Well, that's a little bit out of my expertise. Obviously this is relevant because in the batteries, people are interested in using ionic liquid, ethylene carbonate, propylene carbonate mixtures, and there's been nice work that shows that the flammability of the ethylene carbonate and propylene carbonate is decreased by mixing it with an ionic liquid, and yet you can still have the good conductivity of your lithium salt, whatever version you make it in. But to tell you what an alternative would be to the TFSI or FSI anions in battery applications, I'd say that's kind of beyond my I don't have the miraculous answer to that. If I did, I'd probably be working in that area. so sorry, I can't help with that.
Okay, sorry. Yeah.
Professor Morgan Thomas.
Oh, sorry, I'll sneak in at the end. Can you hear me okay?
Yeah.
Okay. Thanks for a great presentation, Professor Brennecke. So I'd just like to swing around to what Dr. Held mentioned right at the beginning of the question session, where he was talking about ionic portions and neutral portions. So just sort of simplify my question, do you think there is solvation in neat ionic liquids? It's kind of a weighted question, but
Yeah, it's a weighted question. I think there's time average structure in pure ionic liquids. I would not call it solvation.
right, exactly. It's solvation like, right? It doesn't, yeah. To some extent, of course, it doesn't matter what you call it. It's just the effect it has, right? So is there a way from what you've been doing to try to see the extent that influences the structure in neat ionic liquids, sort of extrapolating as you dilute and so on, that kind of thing? Or
Yeah. Well, I think the closest would be that there's been some work, I think simulations, and I apologize to whoever is out there that I'm forgetting who did the work, looking at the sort of the percolation limit as you
right.
Add water to an ionic liquid, and
Oops. We lost Professor John Brennecke, I think. Let's wait a little bit.
But she's here. She's in the session. Oh, no.
Oh.
Yeah.
Okay. She's back.
Maybe muted.
Muted. Okay, I'm really sorry. I'm at the university. That usually doesn't happen. Okay. All right. So I what I was saying was that there's been some nice work showing sort of the percolation limit when where you add water to ionic liquids, and that corresponds very nicely with where we start seeing this apparent decrease in the ion dissociation. So I think there is some correspondence with that structure that you're talking about.
I mean, for me, it's a question of, how important is that covalent bond between a essentially non-ionic portion of the cation or anion and the part where the charge is sort of located? Is that covalent bond important? So if it were possible to take, say, an OMIM and then compare that with an EMIM with an equimolar amount of hexane, and obviously there's all kinds of reasons that wouldn't work experimentally, but that's the kind of idea I'm thinking in that kind of direction.
Yeah, no, that's cool.
Yeah.
That's cool.
All right, thanks a lot.
Yeah, thank you.
Okay. Thank you very much, everyone, for your attendance to this webinar. It was really wonderful presentation. We had today almost 170 people today. That's a lot of people. I don't know if you have some, Professor John Brennecke, some last words.
Well, I just wanted to thank you for organizing this and thank everyone for coming. This was an awful lot of fun, and I really appreciated the opportunity to see some ionic liquid faces. So encourage everybody to keep working, and eventually we'll get out of this COVID thing and have the opportunity to see each other in person again.
Yeah, thank you very much.